Yesterday I tried to explain a bit how things like looking like Motivic complexes come up in group homology. So I tried to explain in detail the weight 2 complex coming up from a computation of homology for SL2. And now for something completely different. So the last bit of the series should now deal with scissors congruences. Which is sort of a completely, at first sight at least, different topic, but where also some complexes looking like Motivic complexes come up. So in dimension 3 we can actually really prove that the complexes that appear there, so like for hyperbolic space, are related to the complexes for group homology of SL2 that I explained yesterday. And in higher dimensions, again, it's conjectural. So I'll try to first say a bit about the history of scissors congruences. So Hilbert's third problem, what the question is, what has been proved so far, and what generalizations exist, and what we might hope for these generalizations, and what is expected there. So in particular, I'll say something that's actually established about the three-dimensional case, and discuss a bit the higher dimensional case, what it looks like, and how it might conjecturally be related to motives. Okay, so 3-1 history. Don't know how, but this is probably something that's known to several among you. So the starting point there is Hilbert's third problem. Actually, well, in a certain form, this was already asked by Gauss. So what's the question? So the task is show that there are two polyhedra P and Q. So here we're talking about a three-dimensional thing. So let me say this precisely in Euclidean 3 space. Denoted by E3. And we want that they have equal volume but we want that they are not equivalent under the relation of scissors congruence, and this means the following, such that there are no subdivisions. So we have these two polyhedra P and Q, right? We're saying, okay, we can subdivide P1 up to Pn, where here subdivision means, well, P is the union of the Pi. The Pi are polyhedra. And whenever I take two such things, Pi and intersect Pj, for I not equal to j, then I want that this intersection doesn't have interior points. Right. Informally, you can cut and paste the polyhedra, cut along hyperplanes here in E3. and paste things together along such faces, and yeah, this is what subdivision of a polyhedron in subpolyhedra should mean in this context. So we can talk about such a subdivision for P, we can talk about a similar subdivision, same condition, for Q. What does scissors congruence mean? It means, so P and Q are scissors congruent if I have such a subdivision for P, such a subdivision for Q, and the pieces are congruent. Hence the name scissors congruence. You're cutting them up into smaller pieces which are congruent. So you want, so that for P and Q to be scissors congruent, there should now exist isometries such that if I take the isometry GI and apply it to this subpolyhedron PI, then I get QI. So what I have now given you is basically the definition of the equivalence relation of scissors congruence. You're allowed to cut the things up into pieces, and the pieces should be congruent via isometries in E3. And Hilbert's third problem asks for specifically give two polyhedra P and Q such that they have equal volume, but they are not scissors congruent. So you cannot cut them up in any way such that you get congruent pieces for the two things. In particular, like, right, yeah, well, yeah, this is, so how did this problem arise in the first place? In the plane, in the Euclidean plane, you don't have these examples, right? So if you take a polygon, you can always cut it up into triangles, and cut the triangles into further triangles if necessary, and in the end you can assemble the pieces so that you get a square. And then this gives you an elementary definition of the area of a polygon, right? Cut it up until you get a square, and then for the square you know how to compute the area. And so this is exactly, so it's, I guess, already in Euclid that if you have three-dimensional pyramids, and they have so they have equal base area and equal height, then they have equal volume. But to prove that, you need to subdivide the pyramids into infinitely many pieces. And Gauss was asking if it's possible with, to do this argument with finitely many pieces. If you could do that, you would get an elementary theory of volume, right? You could take such a polyhedron, cut it up into pieces, and then in the end reassemble the things to get like a cube. And for the cube, you know how to compute the area, the volume, right? So I guess Gauss already expected that this would not be possible, and Hilbert also asked the question, I think, in this form, to show that there are two polyhedra which have equal volume but are not scissors congruent. So yeah, this is based on sort of elementary geometric questions, which, well, then in the end turn out to have quite subtle answers. So, and this was the first problem to be solved. Solved by Din. And so what comes out of this theory is that you get two very specific examples. Say, take T to be the regular tetrahedron. Simplex with the most possible symmetries, and C to be the cube. And these, I mean, of course, we want them to have, so to satisfy the conditions here, they should have equal volume. Say they have volume 1. The claim is it's not possible to subdivide one into pieces and reassemble the pieces and glue them back together to get the other one. Right, you cannot cut up a regular tetrahedron in finitely many pieces to get to reassemble these pieces to a cube. So how do you do this? Of course, you introduce an invariant. Which is now called the Dehn invariant. how does this work? So if you take a polyhedron P, so P should be a three-dimensional polyhedron. What can we do? I mean, this is not the formulation by Dehn, obviously, so it's much too algebraic for that time, but translated into modern language, it's the following thing. So this polyhedron, we can look at the edges, right? And for every such edge, what can we do? So E goes over the edges in the polyhedron. And so for every edge, what kind of metric information do we have? We have the length of the edge. And, well, it's a polyhedron, so the surface is a pseudo-manifold. So at every edge, you have two faces that are adjacent to that edge. And these two faces, there is an angle between them. This is called the dihedral angle, and you can take that, right? Let's call that phi of E. So this is the dihedral angle between the faces of the side, between faces meeting at E, right? Well, for convenience, let me divide by pi, so that I get a, yeah. So, and what we can do is now, so these are two invariants that we can associate to any such edge: the length and the angle between the sides of the polyhedron meeting at that edge. And what we do is we take the tensor of these two things, and then this Dehn invariant lives in R tensor R mod Z, tensored over the integers. Right, this is why I'm dividing by pi, otherwise I would have a R mod pi Z or whatever. Right? So the Dehn invariant is given as we sum over all the edges of the polyhedron of length, tensor, dihedral angle divided by pi. And then, well, you can compute the Dehn invariant of the tetrahedron is going to be 6 times, because of the symmetry, the length of any such any side, any edge. They all have the same length, and the angle coordinate is r cosine of 1/3 divided by pi. So this is a geometric consideration, more or less elementary trigonometry, and the Dehn invariant of the cube is 0. Because, well, the dihedral angles for the cube are rational multiples of pi, and we're tensoring over the integers here. So actually this is true whenever you have a polyhedron where all the angles between sides are rational multiples of pi, the Dehn invariant is going to be 0 for that reason. And then you have to show, well, r cosine 1/3 is actually not a rational number. And then you see there are two different. So there you have two different polyhedra, same volume. They're distinguished by the Dehn invariant. Of course, then you have to prove that this invariant is actually invariant. So whenever you do an operation like this, subdivide polyhedra, move the pieces by isometries, and then reassemble them, the Dehn invariant does not change as an element in R tensor R mod Z. You have to prove that, and then you see that you actually produced two polyhedra, which are not scissors congruent because they have different Dehn invariants, but they have the same volume, thus giving you a solution to a Hilbert's third problem. Right. So, of course, the direct question is then solved. End of the talk. Yeah, but there were several further developments. Of course, you can also now ask, well, what happens now so you have this equivalence relation, namely scissors congruence of polyhedra. And you can ask, how can you distinguish classes? You have invariants, like you have the volume, you have the Dehn invariant. Are there other invariants that can distinguish scissors congruence classes? So the next question is classification of polytopes or polyhedra up to scissors congruence. Can we do that? And the answer is yes. In dimension 3 we can do that. Let me talk about, well, I will keep talking a bit about three-dimensional Euclidean space, and then we'll look at more general questions. No, at this point I'm still talking about three-dimensional polyhedra. But of course you can ask this question for higher dimensional things, and I'll come to that shortly. So there's a theorem of Zidler, and that says for three-dimensional polyhedra P and Q, so if they have equal volume and they have equal Dehn invariant, let me write it with just a tilde. So P is scissors congruent to Q. So there are no more invariants. We really just have volume and Dehn invariant, and that characterizes scissors congruence classes up to. Now, this characterizes polyhedra up to scissors congruence, right? Funny thing to note is that in the plane you actually have an algorithm. Whenever you know things have the same area, you have an algorithm to transform one into the other by basically transforming both into a cube. I think there's at this point no known algorithm that would actually transform polyhedra into one another when you know that they are scissors congruent. Anyway, so
obviously true, right?
Sorry?
Converse is obviously true, right?
Yes, scissors congruence implies equal volume because we're only allowed to move by isometries, and the cutting and pasting does not involve interior points, so changes will have volume 0. And equal Dehn invariant is the thing I mentioned above, that this is invariant under scissors congruence as well.
Is there any relationship between the Dehn invariant and the volume? Like, do they, how orthogonal they are to each other? Is there any other relation?
I'm not quite sure how one could measure that. So I don't know. I'd have to think a bit about how to answer that. I don't know it right now. Okay, so in the three-dimensional case, we get a complete answer. And then, of course, you can ask the more general question and go to other geometries as well. Yeah, well, other geometries, meaning also non-Euclidean geometries, as well as higher dimensions and all sorts of things. Right, so the more general question is now classification of polytopes up to scissors congruence, and we can talk about various different things here. Let me give the appropriate definition. X can stand now for Euclidean n space, the n-dimensional sphere, or n-dimensional hyperbolic space. So look, classical geometries. You can ask this question, of course, in even greater generality, but there are enough open questions for Euclidean spaces and hyperbolic spaces. So I'll not bother with further generality. One thing that is quite useful for computations in this thing, but that will actually not really appear in the talk, is you also could allow yourself the freedom to say, well, here we allowed arbitrary isometries to move the pieces. You can further restrict and say, well, fix a subgroup of the isometries, and you're only allowed to move the pieces by isometries from this subgroup. Right? For instance, if you use only the translations in Euclidean space, then the corresponding scissors congruence problem has completely been solved in all dimensions. Right? So, and then you can make a definition of a scissors congruence group. Well, not quite. It's a bit stable. You see the K-theory ideas already in this definition. So we can define P of xg. Take the free abelian group. So there should be different P's here. So here take polytopes in the geometry X. Well, this basically means, so the definition of polytope for now can just be you have something which you can subdivide in this sense into simplices. And simplices are just convex hulls of points, where for the sphere we have to be a bit more careful than you would want to have the points all lie in a hemisphere and so on. But okay, so yeah, we take the free abelian group generated by polytopes and divide out by relations that are given as follows. Well, we have this thing if the polytope P can be decomposed as P prime and P double prime. Again, decomposition in this sense. Their subpolyhedra, their union is P, and the intersection doesn't have interior points. So this takes care of subdivision relations. And you also have the relation that the class of the polytope P is equal to the class of the polytope GP if G is from this specified subgroup of the isometries. Right? And then you see, well, this is a very obvious thing to look for K-theory things. And actually, these scissors congruence groups P of xg have been identified as pi 0 of a K-theory space in the work of Ina Zacharevich. But this is not directly related to this equivalence relation. So the equivalence relation that you get from these things is actually, as you would guess from K-theory, it's stable scissors congruence. Right? This is not you get a subdivision for each of the things and then you can, and the pieces are congruent, but things here have the same class if after adding polytopes you get such a subdivision. So it's a stable version of scissors congruence, but there's a theorem of Zelev which says that in these classical geometries stable scissors congruence is just scissors congruence. So you have a cancellation theorem if you want. Right? So this actually encodes the scissors congruence classification, and it has the obvious advantage that we're talking about an abelian group here. And so now you can ask the generalized Hilbert's third problem. And in this form, it's obviously still very open. For the classical geometries, so En, Sn, Hn, can we describe P of x, or let me say isometry of x? Further subgroups, that's still other questions, but for now let's stick to scissors congruence where you allow all isometries. A more specific question is, this is probably also based on, I learned this about the what else can there be principle from Aravidas Ok. So it's It's probably based on the what else can there be principle. We know volume as an invariant on the scissors congruence group, and we know the Dehn invariant, and we know nothing else at this point. So we might also ask, are scissors congruence classes determined by volume and Dehn invariant with a suitable formulation of Dehn invariant in higher dimensions that I may get to later. Okay, so this is the generalized problem, and as a next step I would like to say, or like to formulate what is known, because quite a bit is known, in dimension 3. Okay, so we have 3.2, special case, dimension 3. So this follows the work of Dupont and Sar, and of course also other people. The sequences I'll write down, you can also find them directly in Dupont's book on scissors congruences, group homology, and characteristic classes. So the statement is we have exact sequences. And these describe the scissors congruence groups for the classical three-dimensional geometries. So first, the statement for the Euclidean case. So we have P of E3 in the sense up here, where the subgroup G is the full isometry group. We have the Dehn invariant going to R tensor R mod Z. And then, well, we have the co-kernel, and that goes to H1 of SO3 acting on R3 in the natural way, standard rotation representation. And that's exactly the co-kernel. And this H1 SO3 can actually be identified with the Kähler differentials of R over Q. Right, and then you can actually write down exactly from R tensor R mod Z, you can write down the map, and the differential is essentially the differential of cosine of the angle. Yes, absolute differentials. So, yeah. This means in particular not every element in R tensor R mod Z is realized as a Dehn invariant of something, and you can make this more precise. You can write down exactly what the map is, and so on. The other thing is, well, we can describe the kernel of this, but let me write this in a slightly different way. Yes?
It's so special about R3 that it gives you omega 1 of R, because this makes sense for any end, right? Is it one of this?
Yes.
What does it give? Does it give omega 1 of R? I wonder what is this, why this 3 gives you omega absolute differential R?
I guess from the Motivic point of view, you would also always expect that sort of the additive version of Milnor K-theory appears there at the end of the complex for every dimension. But yeah. So I'll write down the complexes later, and then we can discuss a bit further. But I think at this point there is nothing really special about the three-dimensional case. So this end of the complex, I think we can understand in some generality in the higher dimensions as well. Okay, so yeah, to actually write down something about the kernel here, let me reformulate this a slight bit.
And, sorry,
Yeah.
and this map is just something like A times B going to A times dB or something?
I can also write it down precisely. Let me say this is J. And J of an element length tensor, you have an angle divided by pi. This is mapped to L times d cosine theta over sine theta. So that's right. For the kernel, I'll divide out something at this point here. So Z of E3 is the subgroup generated by prisms. Right? I mean, here we're talking about polytopes in E3, but you can just take a polygon in the plane and cross with an interval. This is what is meant by prisms here. And you take the subgroup generated by such things and divide this out. And then you can write down the kernel, and it's another homology group. H2 of SO3 acting on R3, again in the obvious rotation representation. And this is the kernel.
Yes, you're using SO3 as a group, right? Acting on polytopes. So using isometry, I mean, you're using the isometry of R3.
Yes. This is the orientation preserving isometries of the three-dimensional Euclidean space.
Sequence for other groups. Well, I'm sure there are translations or examples.
I'm not sure. The solution for the translational scissors congruence problem is usually formulated differently. So you just write down a lot of invariants and then prove that everything is detected by this. I guess in a paper of Morelli, this is actually identified as, so the invariants come up also from lambda ring structure on a ring of polytopes. So K-theory crops up everywhere. Okay, so what else can we say about this here? So a cohomological version of Sedler's theorem says that H2 of SO3 actually vanishes. So we have a 0 here. And how does this sequence now encode what I told you about scissors congruences before? That three-dimensional polyhedra, volume and Dehn invariant determine the scissors congruence class. Well, in this formulation, if this vanishes, then obviously I can also write the exact sequence like the kernel of the map from PE3 there, well, which I should have written is the Dehn invariant, is exactly this Z of E3. But now these prisms, they obviously have Dehn invariant. They have Dehn invariant 0, and then, because I mean you're taking products of an interval with a polygon, and in the plane you can, by scissors congruences, identify any two polygons of equal area. There's actually an isomorphism from this thing to R given by the volume. Right, this is an isomorphism. And this basically means here the kernel of the Dehn invariant, on this kernel the volume is injective. So, and then the Dehn invariant and volume together determine scissors congruence classes. So this is an exact sequence formulation of the three-dimensional Euclidean case. And now there are the two other cases, hyperbolic space and the spherical things. So let me state the hyperbolic case. And again, the sequence is similar. So we have a Dehn invariant as well. In 3 dimensions, there's actually not much that you can do, right? You have the side, the edges. They have a length because we have a metric space, and you also have an angle between the adjacent sides. And this angle is, again, and it's a number, right? So there's not much that you can do. You can make the same definition for Dehn invariant, and that gives you a map from this scissors congruence group for hyperbolic 3 space. The co-kernel is a cohomology group. It's H2 of SL2C minus. And the kernel, I don't have to actually make a modification like this here. You can really just take P of H3. And the kernel is H3 of SL2C minus. So actually, I mean, what I'm writing here, this is rational cohomology because you can, right. Yeah. This is rational cohomology, and this in the end actually tells you, which is also something non-trivial, that this has the structure of a rational vector space. And I don't know exactly if one could actually see geometrically how to divide by n if you have the class of a polytope. But anyway, so we have this exact sequence, and the minuses here, they signify we take -1 eigenspaces for the action of complex conjugation on the homology of SL2C. And then there's a similar sequence for the spherical case. Namely, we have the scissors congruence group for S3. We have a Dehn invariant, R tensor R mod Z. And the co-kernel is H2 of SU2. Which actually can be identified as, we take H2 of SL2C and now take the +1 eigenspace for action of complex conjugation. And then, again, I have to do a modification similar to what happened here. There's a difference between a 3-sphere and the other 2 geometries. E3 and H3 are non-compact. The sphere is compact. So actually, you could also think of the 3-sphere itself as a polytope. But this is the class that you usually want to ignore. And let me write it like this. You divide out the subgroup generated by the class of S3 in this thing. That's also just a technical bit. And then the kernel, similar to what happened above, is H3 of SU2. Again, complex coefficients, and this is identified with the +1 eigenspace of the action of complex conjugation on SL2C.
The homology are taken with which coefficient?
This is rational coefficients all the time. So. Right, so there are a couple of things I want to discuss about these 2 sequences, because, well, at this point for the Euclidean case, we basically, this basically solves everything. We know everything about the exact sequence. We know what happens here, what the cohomology groups are. This is not the case in this situation, and there are some open questions that are attached to this description of scissors congruence problems here.
What is the role of moving on these sequences? We say that there is no, we don't consider the polytopes of the volume 0, we don't control volume.
Yes, I will discuss that next. I'm coming to that. Because this is one of the open questions. And so we don't know the solution to Hilbert's third problem in these three-dimensional hyperbolic and spherical cases, because we cannot say something like volume is injective on the kernel of the Dehn invariant. And the obstruction to such a solution is exactly a K-theory question. But maybe before that, let me say very shortly, at least in the hyperbolic case here, it's actually possible to say explicitly what's the relation between this sequence and the similar sequence that we saw yesterday. Yesterday I wrote a sequence coming from group homology that said here we had this group PF that was called pre-block group or scissors congruence group. And there was a map to lambda. Well, maybe I just write the sequence again. Right, so we had PF for a field, but now we can actually specialize to PC. And we had lambda 2F star. And then the co-kernel was SL2, homology of SL2F. And the kernel was H3 of SL2F. Again, I'm using rational coefficients here. I should say this at least sometimes I should say it explicitly. So what's the relation between this sequence and this sequence? What's the relation in particular between this pre-Bloch or scissors congruence group that appeared yesterday and this scissors congruences for H3? So how to compare this sequence to the sequence 2 over there? We can say this. So here we're talking about scissors congruences. We're talking about polytopes in H3. Right? You can then take a compactification of H3. Let me write it as H3 bar. And then you can ask, well, look at polytopes in H3 bar up to scissors congruence. And then there is something that is then slightly weirder. You can talk about the boundary of H3 and then formulate some scissors congruence problem for, well, things built out of simplices that lie in this compactification but have all the vertices of simplex on the boundary. Right? And then you can show that with rational coefficients, all scissors congruence problems agree. So I mean you can write down scissors congruence groups for all these three spaces in a sense, and they're all isomorphic via so things induced from these maps. So this means we can go from the hyperbolic space to things where the simplices have all the vertices on the boundary. Now we're talking about three simplices, and the boundary of H3 is actually CP1, or the two-sphere, right? So when we're talking about simplices in here, we are equivalently talking about the classification of 4 points on P1. And this is exactly the link. How you go from this thing here to something like this, right? Because the classification of polytopes in hyperbolic 3 space, and essentially, I mean, so via this it can be related to classification of 4 points on P1, which was the essential thing appearing here in this sequence. And what I should mention as well at this point is that R tensor R mod Z, this is the way we've written it over there with the, so the image of the Dehn, or the thing that the Dehn invariant maps to, this is then actually identified with the second exterior power of C star with a minus action And basically take r tensor theta over 2 pi and map that to minus e to the r wedge e to the I theta. Where would we be without Euler's fundamental contributions? Right, so this is basically then also the key thing. You can then also identify the Dehn invariant with the map that we had yesterday, which basically goes from something here, which corresponds to a configuration of 4.01 infinity z to z wedge 1 minus z. Right, this can actually be identified with the Dehn invariant via these isomorphisms, and everything works out. Right, so this shortly wraps up how the hyperbolic sequence is related to the group homology thing from yesterday, which is good, two different things being the same. And now let me come to this question about volumes. So we can now ask, well, what do we get from these sequences in the hyperbolic and spherical case? Well, this bit of the sequence we can understand fairly well, right? So H2 of SL2 is Milnor K2, and yeah, we can say some things about it. And the question is now, what can we say about this? So I said earlier that the generalized Hilbert problem can be formulated specifically as the question, do volume and Dehn invariant already encode all the invariants that you can have for scissors congruence classes? And this is now again a point, right? I omitted talking about the regulator. What you can do at this point is that before I say open question, so what we can do is we can identify the volume on H3 of SL2C minus or plus. So on these groups here, which appear as kernels of the Dehn invariant, we can identify this thing with the regulator on K3 indecomposable. Because I didn't say what the regulator is, this may not help you very much, but the intermediate step is also very interesting. It works via the dilogarithm. So this is stuff I said yesterday, that this group PF here, right, it was defined as you take the free abelian group generated by points in P1 and you divide out the 5-term relation. And I said that the 5-term relation is given by the dilogarithm. Is the functional equation for the dilogarithm, and therefore the dilogarithm actually gives you a function on this PF. So what you can compute then, and this is also very classical things going back, yes, Lobachevsky and Schläfli and people like this. So if you take the volume of a simplex spanned by 0, 1, infinity, z, right? So this is one of the classes in here. Then you can identify this as you take the argument of 1 minus z times the logarithm of the absolute value of z minus the imaginary part of the integral from 0 to z over log 1 minus t over t dt. And that's the dilogarithm as introduced by Euler of z. Right? You can identify these two things. So this thing here, you plug in complex number. This is a complex function. And what you get here is now a real valued version of the dilogarithm, and that's the function that you can define on this thing, and you can, and that can be identified up to maybe up to factors we can perfectly well understand with a regulator on K3 indecomposable. And I guess this formula here tells you that this dilogarithm function, if you write it down here as a function on this PF, can then be identified with the volume on here. So now let me come back to Hilbert's generalized Hilbert's third problem. For the hyperbolic and the spherical cases, are the scissors congruence classes determined by volume and Dehn invariant? This, with what I said before, is equivalent to is the regulator on K-theory injective on K3 indecomposable of the complex numbers? Well, this, again, is actually equivalent to rigidity. Well, more precisely, in this case, the question if K3 indecomposable of Q bar is isomorphic to K3 indecomposable of the complex numbers. Right? By Borel's computation, we know that the regulator is injective on K3 indecomposable of Q bar. And if we had rigidity, this would tell us the regulator is injective on this thing here, and that would tell us volume and Dehn invariant determine scissors congruence classes. If rigidity is false, then K3 indecomposable of C is significantly larger than K3 indecomposable of Q bar, and then there would be simplices that have same volume, same Dehn invariant, but are not scissors congruent. Right, so this is one of the points where some question arising, in particular in Motivic cohomology, would have consequences in some seemingly unrelated field of mathematics. Maybe one more remark. Yeah? Just a second.
That K3 decomposable is supposed to be countable or something, and the other side is uncountable or something like that?
We don't know. So if they're isomorphic, then K3 indecomposable C would be countable. I think we know if they're not isomorphic, then K3 indecomposable of C will be uncountable. But we don't know anything about the cardinality.
The side is countable or not?
So, I mean, here we know that it's a countable dimensional vector space. But for K3 indecomposable C, we don't know. Right, let me mention again that there is this simplex, the rational simplex problem. You can take a simplex in the three-dimensional sphere and say it is rational if the angles between the sides, so these dihedral angles, are rational multiples of pi. And the question is, are there rational simplices which have irrational multiples of the sphere volume as volume, right? The expectation is there should be such things because the volume here is computed in terms of the dilogarithm, which is a very transcendental function. So you would expect that if you evaluate it as rational numbers, it should be, you should get transcendental numbers or something like this. And but at this point, we don't know of a single rational simplex in the three-sphere which would have irrational volumes. There are volume formulas, but they are expressed in terms of the dilogarithm function, so we cannot really say much about this. And there is a theorem of Dupont and Sar, which I may write here. And they are constructing a three simplex in S3 which such that either this is a counterexample to Hilbert's third problem. So it's not scissors congruent to something which you can write down, has trivial Dehn invariant and same volume as this other thing. So, I mean, so either you can get a counterexample to Hilbert's third problem, saying that there are simplices that are not scissors congruent but have same volume and Dehn invariant, or the other possibility is that this has irrational volume. And I should have said that this is a rational simplex. Right, so it's a rational 3 simplex, so in particular it has 0 Dehn invariant, and then either there's some other simplex not scissors congruent to it but same volume, or this simplex has irrational volume. And if we believe the K-theory conjectures, like rigidity, or Bailenson-Soulé, Bass finiteness, then we must have the second alternative in this case. So, yeah. In a sense, linking these classification questions for scissors congruences to more motivic things at least gives us an intuition of what we should expect if we believe all the K-theory picture, in this case of the classical rational simplex problem. Okay, so maybe what I would like to say now, let me erase these things here to wrap this up and say at least a few words about what happens in higher dimensional cases. So in higher dimensional cases, and the conjectural relation to motives. So what happens in higher dimensional cases? Well, I mean, the thing is, if we want to understand higher dimensions, it's better, I mean, it's always better to have more structure. And so it's not good to look at the individual dimensions, but to look at all the dimensions together. So there's something called Sar Algebra. And let me do this in the spherical case. What does it look like? Let me call it P of S. It's defined as you take the direct sum for all m greater or equal 0, and then you take the scissors congruence groups for all the odd dimensional spheres together. What you get from this is more structure. So you get that this is actually a graded commutative Hopf algebra. Right, so graded is clear by dimension. The product is induced from join of simplices. So you take two simplices, move them sufficiently apart in different pieces of your sufficiently high enough dimensional space, and then take the convex hull. Right, so this gives you some product. There's a co-product, and it's very convenient. This is in terms of Dehn invariance. So if you have a simplex that has n vertices, and these lie in your space, and then you can look at the subset of the vertices and take the subspace spanned by this and take the quotient, and this gives you two simplices in two other spaces, and you can take the tensor product of these simplices in lower dimensional scissors congruence groups. So this would be a general version of the Dehn invariant, and this gives you the coproduct, and the antipode is from spherical duality. So then for Euclidean and hyperbolic cases, you can also do this construction, but sort of if you think about what does the Dehn invariant do, if you take a three-dimensional simplex, you have the length of an edge and you have a dihedral angle. So the angle is always in a spherical geometry. So here, when you're talking about spherical geometries, you get a product and coproduct, but this doesn't work actually for Euclidean and hyperbolic because spherical geometries will always appear. So you only get comodules over the Sar algebra. But then you can write down complexes, let's say co-bar complexes, for these comodules over the algebra. What does this look like? Such a co-bar complex. Let me do it in the spherical case. So you start with, I mean, you can again look at the graded pieces for the dimension filtration and then only look at these things. So we start here with the scissors congruence group for the 2m minus 1 dimensional sphere. And you have the Dehn invariant basically going to m1 plus m2 equals m. And you take the scissors congruence groups for 2m1 minus 1 tensor p of s 2m2 minus 1. And then you go on like this. And the point is, let me write it like this here. ms equals m. You have p of s 2m1 minus 1 tensor p s 2ms minus 1, and you end up in the end tensor m p of s1. And well, this is similar to the structure that I mentioned in the conjectural part of the talks. The structure of these Motivic complexes, if you're trying to write down, you have a Motivic Lie algebra and then write down co-bar complexes for this, the structure was very similar to what we have here. And this is basically now what the conjectural link to motives would look like. Maybe mention, so this is the spherical case, and there are similar complexes coming out of co-bar resolutions for the Euclidean and hyperbolic cases. Right? So you can write down these complexes, and then everything you would want to know about the generalized Hilbert's third problem and so on is encoded essentially in the cohomology of these complexes. In particular, the question, are scissors congruence classes determined by volume and Dehn invariant, concerns the kernel of this first map. You would want to know that on the kernel or in the respective cohomology group of this complex, you can define the volume, and you want that this is injective. So, and then Goncharov's conjectures is, well, in this particular case, let me say hi of now d of s 2n minus 1 should be the Dehn complex that I wrote up here. All right, this is this complex, and this should be, you take the graded pieces of the gamma filtration of k2n minus I of the complex numbers, rationalized, and then you tensor with epsilon n and take the minus 1 part. So this here is the integers with the Galois group of CR acts by minus 1 to the n. So this would be the plus part in the three-dimensional case that I mentioned, and the minus part in the five-dimensional cases, and so on. Right, there's a similar conjecture for the hyperbolic space. The corresponding Dehn complexes for hyperbolic space should also compute. Sorry, I missed it up. So this should be plus here, right? Plus computes the thing for the sphere, and minus the corresponding minus part of graded pieces of K-theory should compute the cohomology of the Dehn complex for the hyperbolic space. Right, and then basically if we had these conjectures and had rigidity for K-theory, this would give a complete answer to a Hilbert's third problem, because then the volume identified with the regulator on the corresponding K group would be injective on the kernel of the Dehn invariant. And maybe the last word, in the Euclidean case, there's also a conjecture of Bloch and Goncharov that says the homology groups of the Dehn complex for the Euclidean case should basically be relative Motivic cohomology for the dual numbers relative to the ideal T. So this should be the answer in the Euclidean case. Okay, but all of this is conjectural. I'm sorry that I went over time every talk, but I hope that I have explained some of the interesting links between Motivic cohomology, scissors congruences, and group homology in these few talks. Thanks for the attention.
Are there some questions or maybe comments?
So you have this Euclidean hyperbolic is spherical. So it seems that I'm confused about, so if you take Euclidean case, it somehow gives you the K-theory of the ring of dual numbers. And in the spherical case seems to be the higher Chauvers. What happens in the hyperbolic case?
No, it's not the. It's only some part of. So I mean, the spherical case and the hyperbolic case belong together. They should be related to the Motivic cohomology of the complex numbers. So you have the complex conjugation action on this, and this splits it into plus and minus part, and this is spherical and hyperbolic things.
I see. So they are just kind of two parts of the same thing.
Yes. And then sort of if you look at the Motivic homology of the dual numbers, so everything that's sort of in the kernel, so relative to T, so everything that's sort of strictly infinitesimal should come from the Euclidean case, and then the corresponding part for just coming from the complex numbers, this should now be a combination of spherical and hyperbolic together. So in a sense, the dual numbers should actually encode scissors congruences for all the classical geometries.
So this may be a too far-reaching question, but what's the relation with this conjecture and the Beilinson conjecture? I recall that to prove this conjecture, one of the first problems was to build elements in Motivic homology. If you have this conjecture, can you build these elements? Or is it... And for example, there is the Polytopes, which I think appears like this, but
well, I mean, if you had this picture, this would, I mean, to construct elements in Motivic cohomology, you would then have to construct elements in here. So you have to construct polytopes where you can show that the Dehn invariant is trivial. And that may again be complicated because, I mean, so at the very beginning, when I talked about the regular tetrahedron, you had arc cosine of 1/3. And to show that the Dehn invariant there is non-trivial, you had to say this is an irrational number. So it may come in when you want to show that a certain polytope that you construct has trivial Dehn invariant, that you actually have to show that some number is rational, but then depending on how the number appears, you might not know enough about this number to actually show that it's rational. So that, yeah, this is the conservation of difficulty.
Some more questions? More comments? Let's to speak Matthias once again for wonderful course on cohomology, Motivic cohomology, group cohomology, and scissors congruences and related relation of Motivic homology to the very, very classical and simply stated questions.